Bildschirmfreigabe screen. So
And should we hand in the whole project or just source files?
well, the whole project are this. Well, the whole project are the source files plus the solution and the project file.
Mm-hmm.
I would just put everything.
Okay.
But of course, don't hand in the intermediate files generated by the compiler. So nothing in the x64
Mm-hmm.
directory or the .vs directory also not, because this is
So I can
just
do a clean before and then,
yes.
okay.
Okay, so let's see. Let's open it again. It was a thread race. Just looking the attendance list, which I need to maintain as well. Okay, so you can right click on the project properties, Qt project settings, and here you can select the Qt version that you want to use. And as like normally, the default would be just the path I now marked. I have here the 632 underscore because I might want to have different versions of Qt on the machine. And the Qt versions you can configure on the extensions, Qt tools, Qt versions. Currently I only have the one, but if I would to add a second and a third one, then of course I would need to differentiate them and I usually just prefix the version number before the compiler type and platform. So this is a quick way to fix this if on your system the Qt installation is named differently. Okay, any more questions? Okay. Okay, if there are no more questions, well, we should wait at least 2 more minutes, maybe more people will appear. From then, in the meantime, I can tell you what we'll be doing today. So, we have already taken a look last time on Qt, which is rather not very low level, quite the opposite, but it's something that's extremely useful to create quite nice UIs. And since last time we have already taken a look on thread creation and simple thread synchronization, now what we will do will be we will take a look on how we could do the same things. One using the STL library, which is available, which this functionality has available since C++11. All the C++ revisions did not have this, and how we can do it using only Windows facilities, so in a way that you could use with an arbitrarily old C compiler like Visual C 98 or something comparably quaint. So that will be the low level part. So let's quickly start with this. We'll create a new project. Okay, 5 people. We'll create a new project. In principle, for simplicity reasons, we could create a Qt console project and just don't use any Qt things, but I guess we don't need it. Let's really go with a normal console project. Okay. And let's start with the standard Windows way of doing things. So to do anything with the typical Windows headers, we include just Windows H, which includes most of the headers that you might use on everyday basis. If for some more specialized things, other headers are useful. If you want to do things more related to the anti-kernel of modern Windows operating system, you would include WinKernel H, which then contains headers for anti-DLL and stuff like that. But just to create a few threads, it will be enough to just have Windows H and use that. I guess that should be it. And the whole Windows API is just plain C, so it does not most of it, or even the whole thing, does not contain any C++ parts. So there will be no class that represents a thread. We will only get a operating system handle that represents the thread within Windows. And therefore, if you want to run a thread, you will need a way to somehow pass an entry point to the new thread that Windows will create for you. So for this, we will define as a entry point function with the return type double word win API, and let's call it my thread. And the function has to take an argument lp void, so a arbitrary pointer on something, which we can call param. And this value we will be able to pass to the function when it's created in an own thread through our thread creation function. So for now, we make it as simple as possible. We just return 0 and put a breakpoint here so that we see that this will work. And in our main function, we use the create thread API. Create thread, where we can pass various parameters. So the security attributes are for us currently not relevant. We just pass null. We leave it also at the default stack size, and the first relevant argument is the start address, which is our function name. Then we can pass some pointer to our thread. So let's quickly create some object as and value 1 and value 2. Value 1 is 1 and value 2 is 2. Just something simple enough, recognizable. And we can pass this pointer directly as the argument. Then we need creation flags. Here we could, for example, specify if we want the thread to be created in a suspended state, meaning it will be created, Windows will know that it's there, but it will not yet execute any code. In some use cases this is useful, for us no, so we just pass 0. And then here we could retrieve the thread ID if we would want it to. The nice thing about the thread ID is that if we have this number, then we could open a handle onto this thread from any other process within Windows, assuming our security descriptors allow for that. But since we are not interested in the thread ID, we just pass here null, and the function returns as a handle to the newly created thread. And if it returns 0 or null, then something went wrong. So in this case, return -1 and printf fail. Return 0 is on success. And what we can do is we can wait for the thread to finish. Wait for single object. Wait for single object. We can pass the handler and how long we want to wait. If we pass -1, it will wait forever. There is also, I think, a preprocessor definition infinite, which if we just go to the definition is just the -1 as double word. The nice thing in Visual Studio is that if you hold down Control and click on something, then it brings the definition, or if you are in it and press F12, it does the same. The F12 is like a Visual Studio sort of doing things. The Control click is often used by many other IDs. So it's nice here. And the last thing we have to do is we have to close the handle. Otherwise, there will be a resource leak. Of course, if we terminate the program, all handles held by it will be closed by the operating system anyways. So since we terminate anyways, it would not be strictly necessary. And if we run the code now, we will notice that we end up here. But maybe before we do that, we want to be able to somehow make meaning out of the param we got. So we can copy some code from here, then do some casting. Okay, And here now we have our param, so we can tell the thread how to operate. And for example, Qt uses this mechanism to just start the thread and pass a pointer as parameter to the QThread class, and then on this the run function is executed. We can maybe quickly implement later such a behavior here as well, after we have shown that this works as expected. Okay, and you see we are here, and if we go to the okay, that doesn't show that debugger Windows process threads. Can we move this maybe here? Okay, we see here that there are a couple additional threads which were created when the process was loading libraries, but one here is the main thread, which is the main function, and the other one where the arrow points, we are here in our own thread. The two others, as said, are created automatically by Windows when loading DLLs, such that the libraries can be loaded in parallel, which improves performance. Older versions of Windows just loaded one library at a time, and they will be automatically terminated after they were not used for a short while. So if you would have here probably a sleep for 10 seconds, then we would not have seen these additional threads, but we don't care. So at this level, as you see there, it is plain C code, and you don't need C++ to create threads in Windows. But now what we'll do is we will improve this in a way that allows us to have an object and a behavior more like we saw from Qt. So make a class, see my thread, public. We add to it some constructor, which for now does nothing. We add a virtual destructor just in case. We add a function start. And we make a void. Well, it doesn't need to be void, but why not? Let's do it. Double run is equals null. So the function here is abstract, meaning that you cannot create an instance of CMyThread directly. You need to first derive something and then provide a body for run. And we will need some internal function also. Up here. Prods devote palm. And when we start, we perhaps want to be able to pass. No, we don't want. We will make it just like Qt does it. So we will also need to keep track of the handle. This will need a body later. So thread, we initialize this to 0, and if this is not 0, then we close handle. Windows is a bit. The Windows API is a bit inconsequent with regard to the available functions to do things. For example, the close handle is provided by the anti-kernel library, and there is another function called just anti-close, which is provided by the anti-DLL, and normally just the close handle calls anti-close. So for many functions which you might see as the typical functions you're expected to use in Windows that live in the kernel 32 library, you will see anti-DLL versions, which usually, so in this case they don't have different parameters because they're trivial functions, but like create thread, create file, open file, etc. The kernel 32 versions are usually wrappers for the anti-DLL syscall, then which then directly transfers control to the kernel to the Windows kernel. Okay, but here we have our thread, and in start we will have this line. This we need as well. Of course, here we need the run prods, and here we will pass this. Why is that complaining? Needs to be static. Why did I swap them? I swapped them. Oops. That's the right order. Okay, so this does this. We don't need a return value. Now we need a body for this. One. Run. Et voila, that would be our abstract C thread. And now let's create an implementation. Okay, probably should not have called this my thread, because then I would want to. Let's just call it thread 1.
Excuse me.
Yes.
What does dword and handle mean? I'm not familiar with these.
dword is just a preprocessor macro, which it is basically short for double word, because historically a word was supposed to be 16 bits in Intel architecture, and with 32-bit operating systems you needed to use 32 bits most of the time, so they just called it double word, and it is just an unsigned long. If you would write unsigned int, it would normally evaluate to the same internal data type. And the handle is again another type, which is basically just a void asterisk, so a pointer to something arbitrary, just a memory address basically. Although a lot of handles that are returned by Windows are not true memory addresses, but just numbers picked from a pool which the kernel internally can then associate with the actual objects.
Okay, thank you. But then how does dword and win API fit together? So if one is an unsigned long and then this is...
No, you asked what handle is. Win API is yet again another thing. It specifies which calling convention to use for the function. In this case, SCD call, because this is the standard calling convention for all Windows APIs. On 32-bit in 32-bit code, as it's normally used by the MS Visual C compiler, has different calling conventions depending on where it is used, and hence this preprocessor macros have been introduced. In 64-bit code, as we are using now, everything just uses one calling convention, so this calling convention specifiers on 64-bit Windows are just ignored. But if we would have 32-bit code, then if you would forget to add the Win API to your function, then the function would end up with a different calling convention, and then the program might crash or behave in unpredictable ways.
So is the calling convention precise how the structure, how the stack will look like in the called function? Okay.
More questions? Okay. If we don't have more questions, then we continue with this. So here we can implement the body of our function. Again, return 0. And this is pretty much all we need. We don't need to say that this for good measure. Now instead of... okay, we might also want to have maybe a function to wait for terminate. Wait for finish. Qt also provides such a function. There we can put this in. Yep. I mean, ideally we should check if this is not null. Then wait for finish. Yes. Okay. So instead of doing it by hand, we can now just create an object of type thread1. Thread1 and start it. And this more or less behaves like you have already seen last time in Qt. Okay, something's wrong. Param. What? That should be right. Palm. This the thread terminated. We need to add here the wait for finish. Otherwise the thread terminates and the memory goes out of scope and we have a problem. So we need to wait for it to finish. And I think we forgot the breakpoint. No, we had the breakpoint here. Suck. And it works. And now the nice thing is that instead of having to make some temporary structure to pass arguments around, you can just add some of your arguments directly to your object, and then you can access them within your run function on the object directly. This is quite nice. Now, the other method to create a thread, which is available in more modern flavors of C, of the C++ language, is to use the standard template library thread function. So let's include that. Maybe first let's maybe label those things. So this will be then here we have typos. And we can leave this in here, maybe for reasons of well niceness. Let's add here val1, val2, and or we make it public, then we can modify it from outside. Okay, then plain C we have this. Okay, nice. Now let's include hash. And let's quickly see if we have the right C compiler version set, but I assume that by default that should be okay. Even better, we already have C 13 as the default. It doesn't even offer you C11 anymore in Visual Studio 2022. All the Visual Studio versions allowed you to select all the versions of the C language. Generally the nice thing is that you can compile arbitrarily old code with a newer version. So in this way mostly there is no reason to use an older one. There might be some very exotic language constructs, or if you used names in your old code which in the newer code then might be used by something else, then you might need to update it before switching to a newer compiler version, but generally this is not necessary. Okay, so we have included our thread library, and here let's make another example. SDR thread handling. So thread method, or let's call it thread1. Yeah, let's call it thread1. And this thing will need a function. So it's not as much object oriented as Qt, but it's still quite nice. So void, and we will create a second thread with a different parameter set. Let's say that it just takes an x, and here it just returns. So that's good. So thread1, and we can and this will automatically start the thread, so there will be no opportunity. So as said, with Windows we could create the thread in a suspended state, but with Qt, when you create the object, the thread, it does not run as such. Here, as soon as you create the object, it will run. And if you want to wait for it to finish execution, you have to use the join function, which, well, the name is not Windows-ish. It's from more the Linux part of the world. There, usually, when you create a thread, or another process, you call it fork, and if you wait for it to terminate, you call it join. Because the idea is that you have some code execution, and then it splits into two or multiple, and then if one of them terminates, then in a way you have only one line, so it's joined and going again. So I would have wished that maybe that they would use a more generic description, but oh well. So here we can add maybe a comment. And the nice thing about this thread thingy is that you can use it quite nicely to pass arguments. So if we have a function that takes an argument, then here we can just add the argument in thread creation, and it will be passed, and we can have as many arguments as we want, well, within reason, which then will be passed to those functions. So we can put two breakpoints here. Now when we run, we'll run through all the breakpoints we had, since all the code is now active. First our C example, then our C++ example, and then we get into foo and into bar. It's actually kind of random that we actually managed to get into foo before bar. Depending on the system load, that might have been different, since both of them, as soon as they are started, it's up to the operating system scheduler which one will be executed first. Of course, assume if this would take longer to execute, then there is a large chance for foo to be already finished. So in principle, for a lot of modern programming, threads are generally very important, because you are not going to get any faster CPUs anytime soon, at least not substantially faster. I mean, 20% every 2 to 3 years, it's more or less the best you can hope for. But what you will get more and more are cores, so it's important to design your applications such that they can take advantage from as many computing cores as possible. And that's also why modern STL versions support so many thread-related functionality. So they not only offer you now a facility to create threads, just using the standard library, and not needing to resort to use operating system specific functionality, but the standard type library also provides a lot of synchronization objects which you can use. So the last time we already taking a look on a mutex, and for example here there is a similar thing that you can create, but for that we will create a new project to test the different we can stick to the same project, but it would be, I will create another project because it would be nice to compare later the performance of the different mutex implementations. So between using native Windows operating system facilities, then between using the standard template library implementation, and finally compare it to how Qt does things, because they claim they are very highly optimized. So we'll create a Qt console application. We just call it MT test, or test MT, test multi-threading. That's a nice name. Test MT. Once it's created, we'll just copy the code from here, since well, we don't have to. We can just stuck to use one of the thread creation types. The least typing I think we have when we just are using the standard template library method. since since you can do it without needing to create a derived object, and you don't need to specify so many parameters and then think about how to pass arguments around. So I guess in this function we'll just stick to this. One important thing to say at this point is that while the different synchronization mechanisms will have a significant impact on the performance of your application, which method you are using to create threads is completely irrelevant. Internally, if you look in this, for example, then it will just call at some point create thread anyways, and Qt will do the same thing, because as long as it runs on Windows, it will have to use the same mechanism. And at the same time, the additional computational overhead, if you for just a few function calls to wrap everything nicely up, is mostly negligible. So that's that. And of course, if you are using synchronization objects, there you have much more opportunity for much more overhead. Hence, we will try those mechanisms out. Yeah, let's leave that in. And let's create a couple. Let's include a few things. Hash thread mutex q mutex and Windows. Okay. So since we already seen how qmutex works, let's not repeat that. We will, however, need some threads, so let's create a couple. Let's create some function for it. My thread, which does not take any arguments yet. And let's start a couple of those for okay. And and 10. Let's create 10 threads. So in this case, we would then want to use the macro array size to just go through all the threads. Why is it complaining? Okay, it's array size, not just the short way. And it's implemented quite okay. Yeah, there are different ways to implement it. So this is apparently here a bit more sophisticated by now, but like old implementations. So if we would want to have an own R size, oops. The simplest way to do it is something like this. So we have our argument, and then we take size of x divided by size of x0, and the whole thing in brackets just to ensure. So this is a very simple implementation which just does the same thing as the already provided implementation. But of course, since modern headers usually have such a function, it is recommended to just use what's available instead of every time having to define your own. Okay, so threads from that will not work because it already starts them, so we need to do it differently. That needs to be like this. So thread from I is equals new std thread, and it takes our my thread function. Okay, this will just start 10 threads. We can okay, let's give them an argument. Int e. Let's give them an argument. And you might wonder how it works that the thing that you can add multiple arguments. We can check if we can find it. So in principle, it implements you a variable argument function, so you can pass as many arguments as you want, and then it passes them to the function that you have here. This is quite a nice mechanism that you don't need to think about your own argument passing. Okay, so I'm %d. Okay, so now if we run it, we'll just see on the console 10 threads saying who they are. That's just for starters that we have some threads that can do something. Zack. As you see, the order in which they manage to execute code is quite random, so it is not like 1 through 10, because they were just created and the operating system then scheduled them however it's saw fit. It's very important to think about that when you have threads, that you cannot rely on any particular order of them being able to do things. Okay, and now we will, let's say we'll make a variable. Okay. Let's make a in 64. Oops, that we can really go as high as we want. Then we need a mutex. M Q and here we just okay, for we just put an endless loop. Oops, lock unlock, and then inside the loop we just increment our function. Something reasonably simple. Okay, let's call it Qt, because it uses the Qt mutex. And then can do the same thing. We later change to different types. Std. Obviously, you cannot have like multiple mutexes to guard the same resource. You always should use one mutex. So to be on the safe side, we should ensure that this is clear. And then for this one, generate another one, stl. Then we need to include mutex already included. Okay. Std mutex stl. Let's YAML lock. So this should work as well. Now I see we have not run it, so let's see. I mean, if we run it, we're just boring, but we can run it, and once it's running, just put a breakpoint within it and see how far it counted up. That's a good idea. So they are now all running and doing things. You can also see when we see the task manager that it already needs a lot of time to open because the system is busy. All the cores are running at full blast. If we put now a breakpoint here, we see that we have counted to however many billion that might be. 1, 2. Okay, not even a billion, but a few 100 million. So that's quite nice. Okay, and now we will take a look on how to do that the Windows way of doing things. So we'll again create another counter win1. I will do here like Windows 1, Windows 2, Windows 3, and so on and so on and so on, because for Windows there is a couple of different mechanisms that can be used to synchronize threads. So first one is called a critical section. No, not M, that should be G. Global thing should start with a G. I mean, it does not really matter. It's just nice if you see some variable and you know where it belongs to. Okay, so that was fixed. That was fixed. Okay, and this critical section thingy is, as all the Windows things, more a low level sort of thing. So it needs to be explicitly initialized. So let's see. Let's comment this out. Just create Q thread qt comma 1 stl thread is was stl. No, it was my thread. std. Okay, that's not consistent. stl. So std is an abbreviation for standard, and stl stands for standard template library. So that's why there are two. Actually, we could also change that maybe here to take a Stern name instead. %s zack, %s zack. So we can actually give them names like qt stl, and then we'll have win1, which we don't have yet. My thread win1. Yeah, and we need to initialize the critical section. So it wants a pointer to our critical section. Okay. Those we can comment out for now. This we will remove because we don't need that. Okay. And here we copy this part, and then actually we could have just written the name here as not as a parameter. Well, too late. So enter critical section reference critical section, and leave critical section. Then we use our win1 counter. Large L, and this should work as well. Let's quickly run it. So a critical section is only usable within one process. Oops, something is wrong. Other Windows synchronization primitives are implemented such. Okay, it does not like strings apparently. Why? Okay, it might not like this. Alright, this should be const string. That might all be all. Zack, zack. Yep. Okay, and after some time, let's enter here and see. Huh? Wait. That should be running. Why is it not? Does not look promising. Oh wait, did I put the I put the breakpoint wrong. And we counted until we counted quite high. I think this already looks well higher, and of course we have not the same time for all of them, so this of course is something that is very unprecise at this level. Okay, so this one was one method. Let's comment this out. Maybe we should make like one code block per each method. And now the next, so what I also was saying, this critical section is something which can be only used within one process. So you can use it to synchronize threads of one process, but you cannot use it if you would want to synchronize any sort of shared resource between two independent processes. And Windows provides other synchronization facilities which, while they mostly are used within one single process, they can in fact be used across multiple processes if they have been first given a name or have been copied to another process by handle. So Windows has a couple of those synchronization objects. It has mutexes, as we already know, but it also has a semaphore class which allows a counted reference. So, for example, if you want to allow, let's say, 10 processes at the same time to access one object, you could use a semaphore for this. Of course, this type of synchronization is not suitable if you if for the same thing for what you would use a mutex, because if more than one element can access and write to the same resource, then it can screw it up. But for example, if you would want to say within your process or your group of processes that only 2 of them or 3 of them at the same time are allowed to read or write from the hard disk, because you don't want to generate too much parallel accesses to the device. I mean, with SSDs it's no longer so critical, but with a mechanical hard drive, you would want to have as little concurrent accesses as possible to maintain a good performance. There, for example, it would be a good use case to use a semaphore such that all your accesses will be synchronized to not more than, let's say, 3 or 5, although that already is a lot for a mechanical hard drive, to be honest. So let's anyhow proceed with the Windows ways of doing things. So first of all, we will need a handle to hold the mutex. Handle G did we use mutex? We use qmutex finmutex. Let's call it Windows mutex. We can initialize this to 0, or rather we should write null, although as I said today morning, if you just look on the definition of null, it's just 0, so it is really the same thing. Okay, so now we can create it using the function create mutex. Then we specify some security attributes. Again, we don't care, so null. Initially owned means whether that will be locked when it's created or not, so we say false. And then we could specify a string containing a name. If we would do that, then any other process in the system could open this exact mutex using the name string we have provided, assuming of course the security permissions allow for it. So, but here we don't want that, so we just say null, so it will be an unnamed mutex. And at some point, once we are done, we are not waiting for anything, so we need to add, okay, then they don't terminate, we just put all the weights at the end. For this one, wait, STL thread. That one should be called win thread. Win1 thread, actually. And then we need to create the second one once we are done with creating our object, so that will be the win2 thread. That will be the win2 function, which we don't have yet, so stl. Okay, stl win1, win2. Win1 is commented out. And here we need to close handle on our mutex. The section, as far as I remember, no, there is one. We also will need to deallocate. So for the win1 case, so let's separate this here. And init section and the pointer to it, but since this is closed, okay. we need this function, so let's start with this. Thread win2. Name is win2. Okay, did we forget? No, we didn't forget anything. So at this point we can already start using our mutex. And we do it using the wait for single object function. Was it like this? Wait a second. Yeah. So, and we need another counter as well. So win2, counter, this and this. So wait for single object. Zack. Handle is mutex. Timeout is forever infinite. And once we are done, we need to unlock it. So we use release mutex, handle, and voila. Okay, let's remove the unnecessary lines. Let's run it. And then once it ran for a couple seconds, let's put a breakpoint in and see. Okay, how much? Yeah, that doesn't seem to be very performant. Which is good, because one of the homework assignments for today will be to benchmark those different synchronization methods. So to make it, well, I will describe the exact details once we are done with all the tests. So we can comment this out. Yeah. So this much to just the generic types of synchronization objects that you might be using. For Qt, you might remember we had this QMutex locker, which just does this lock and unlock automatically for you. So this could be used instead of the 2 lines. And for STL, they in fact provide something similar. What was that? Scoped lock, I think it was called. std scoped lock. What does that need? What does it want as parameter? Wait, we might not have this in the scoped lock. It's only available in C17 if I remember correctly. So we might need to change the compiler version in the end as well. Let's quickly check that, but there should be already some of those primitives available for the
lock guard, something like that.
Lock guard, that sounds also good. Could be available. Is that already available in C11? Yes, it is.
I think so.
Let's try that. std lock guard. Yes, we have that. And our lock guard should want just a pointer on the mutex. So where is it here? Yep. It needs to, no, it knows the type, so that should be working just as fine. We can quickly test it by uncommenting our STL version here and running it. Yeah, let's see what was it here. Zack. Yep, it works fine. So of course for the other Windows-ish ways of doing things, you don't have such a lock guard. But those things are not difficult to implement, so we can quickly implement such a thing ourselves. That was so let's see. Let's call it grid guard. Section path. Then we just enter the critical section in our constructor, and we make a destruct. We will need to cache that. We will need to cache that. Create section. Yep, and then we can just have the unlock or the leave critical section here. So, as you see, it's very easy to make very helpful own objects in C++. Let's quickly test if this works as it should. I'm commenting this. Okay, 2, zack, perfect. Yeah, let's maybe by default use this in all our scenarios, here and here. Then here for the mutex, that will be a to-do, so one homework. And this one I will rename to section guard. That should be easy enough. Okay. Zack. Good. Yep. So that, why is it complaining? It should not be it's complaining because we missed the semicolon here. Okay, and the other part of the homework now will be to run multiple threads of each type. So let's write it down. To do, it will be to do 1, it will be to do 2. Yep. How many is not too many? I mean, that will put a high load on your computer, so expect it to make things slow. Run 10 each type. Of each type. Oops. So do we have 40? We have 4 different ones, right? Yes, 40. Exactly 10 seconds. Each thread it's always called gcount and then something underscore 10. Okay, and to do bonus feature work. Another 40 threads, not the locker. They call it locker or lock? I have to be consistent when I make homework out of this lock. I will call it lock. Lock. We'll call it a lock. Yeah, so we will see here how much overhead, first of all, such a simple helper object generates, and then how much overhead the individual implementations of STL and Qt bring. My gut feeling is probably not much, but we will see. It's a reasonably easy optional bonus task. Okay, any questions at this point? No questions? Okay. Then let's take a look on another thing that is also quite useful, namely mechanisms to allow a thread to be suspended until something happens the thread is waiting for. So we already have seen some of those here with this join command, well, function, join function, and this is of course quite useful. You can do a similar thing if you create a process, that you can wait on the handle of the created process for the process to terminate. But often you might want to wait on more specific events that you can trigger in more precisely controlled way. So we will create here a new project. Test empty. It will again be a Qt project, since we will want to compare also the behavior of the Qt thing. So let's call it test. Well, I'll call it event, but it's not really an event. Test event, or rather test condition, test wait. Let's call it test wait. That's reasonable. Okay. Next, finish. Okay. So we will again need some thread. Oh, my thread. Thread. My thread should not be the same name. My thread, and my thread. We don't care for join. We'll be doing a different synchronization method. So, obviously, one could just use a spin lock, which is not very efficient. Actually, we forgot to use here a spin lock in this list of operations. But I think since normally, unless you're writing kernel drivers or stuff like that, you will not be using spin locks anyways. I think it's fine to not include it. Also, the spin lock would either be extremely slow or put a high load on the operating system, meaning that the other all of the other methods would get worse results. But the important thing to keep in mind here is that a spin lock is not something that you would use in production code away from the kernel, simply because it causes a very high CPU load. But here for the task of just waiting for an event, if we know that it will take some time, then it would be a valid option to use a spin lock. So in the simplest way, we just make an int m lock or let's do it at least somewhat properly. std atomic, should be able to specify the type integer, not mg spin lock. Okay, we can initialize this to what was it, set store 0. It will be initialized with 0 anyways, but for good measures we ensure that it's definitely with 0, and then in our thread we make example a, okay, we need to include the Windows header. So we can use normals, not capitalized. Oops. Huh? You wrote sleep with 2 e as you wrote. It's wurscht. I need to okay, then we should have the normal sleep function with 100. Why is it complaining? Was it capital S? Okay, it was capital S. The normal sleep function for, let's say, for a second, and then we want to unlock the spin lock, so we store 1 to it, and then we wait for another second, and then we terminate. Okay, and here now we want to wait, so while spin lock load is while it's 0, sleep for 100 milliseconds. And so let's say here, let's add our qdebug. Let's start it. Starting, because it's not yet started. Now it would be started, but we don't care. Now we say waiting, and here we say, well, success. Reasonably simple. Waiting, success. Yeah, works fine. And now if we would want to do it without using a spin lock, the Qt way, we would need a few more things. We would need a qmutex and a qwait condition. Oops. Wait condition.
I'm sorry, what is this atomic? I missed it.
So atomic means that the operation is guaranteed to be executed and not be interrupted by any other thread. When we just use it to store and load, it's rather boring, to be honest. But if we would want to implement a own mutex, we would use test and set to ensure that we can atomically change the value only when it was not yet acquired by someone else. You can review the source code from last time. Okay, quickly open that here. Recent solutions. Where was it? Was it here, perhaps? Where I showed such a somewhere thread. Oh, that was another file. Then it was in one of the files from the last time. We showed that, if I remember correctly, 1 second. So that was, where is it? So it was last time demo. Yeah, one of them. So then it was in demo. Okay. So okay. So thread. And here we used okay. So we used the Qt version of it, Q atomic integer, but from the way it behaves, this Q atomic integer is the same thing as our here used atomic int. The main difference is that Qt just has a couple of atomic types, like atomic int, atomic pointer, and I think that was already it. While std allows you to more or less turn a couple of types into atomic operations. And here, as you see, for this operation, we use the test and set semantics. So it tests whether the content of the variable is 0, and if it is 0, then it will set it to 1, and if this succeeds, it would return true. If it fails, because some other thread already set this to 1, then it would fail, and then in this loop it would spin until it manages to acquire the lock.
Okay, so these atomic variables are just used to lock the thread from being executed.
The atomic variables are used to operate on values in a way that another thread cannot interrupt the operation somewhere in the middle. So it guarantees that if you use them across multiple threads, that every operation will be fully executed, and you will not be able to access some inconsistent state of memory that might be left while a more complex operation is being performed.
Okay, thank you.
So we can close this. Well, yeah, so we need those two. So we will. What was that? So here in this we can just quickly let's start with the waiting part. So for the waiting part here, so we started here, we will want to wait the other way. So we need a mutex log, and then wait condition wait, then the pointer on the mutex, and then we do something if it's success, and then we can unlock the mutex. And here we can wait condition. We don't need anything, just need this mutex. We can select between wake 1 and wake all. So if you would have multiple threads waiting on this condition, you could wake all of them, or you can only wake one of them. So we will go with wake 1. And this will more or less behave the same way. Once we run it, it will just wait for a second, and then it will say that it successfully waited for this thing to happen. And it's compiling. Okay, it worked. It said success. Now we can take a look on how this would be done on Windows, or rather how it is done internally within Windows by using this wait condition. So can okay, maybe actually we should do it the same way we did it last time, so that we have different function. My thread qt, then my well, that's just my thread spin with the spin log. Then here we will have my thread qt with the qt wait condition. Okay, then we should to be consistent, the next thing we do should be my thread STL. So let's do this next. In STL, the provided thing is also called wait condition, as far as I remember. So let's see if that is so. Just have to check quickly. Instead, because there are so many different versions now with the different compiler versions. So we have to see if that's available in C11 or if we need something newer. It should be, so that's it should be available in C11, so let's try. Hash include condition variable. It's not quite wait condition, but similar. I will still call it wait condition because that's a good name for it. It likewise to Qt needs a include mutex. It will need a mutex thingy, I think. So here mutex. Yeah. I'll just stick with this naming. Okay. So within our waiting function, we have our condition variable wait. Do we need arguments actually for that? Yeah, we need some. Clock lk mutex. The thing wants this. Well, it wants a pointer on this thing, anyways. No, it wants this by reference, and then it wants a lambda. Semicolon. It wants a lambda return. That should actually just work or return 0. We don't need anything else in here, I think. So in this sense it's easier. Well, actually we could use here for Qt also a thingsboom star mutex locker instead of locking and unlocking that manually. So actually maybe we should do that for reasons of everything looking more the same. Plus it saves us on the unlock further down. We don't need this line then, so this is it. This is that, and now we need just to implement here our to signal it. So we have our variable wait condition. Notify again, notify one. So you see, it's quite. The names are not very similar, but they do the same thing. So you have notify one as you had wake one, or you could have notify all as you had here wake all if you want multiple things to be notifiable. So let's quickly try if this works, and then we will do the manual Windows way. Okay, so waiting. That doesn't work. Interesting. Why doesn't that work? That is not good. Or maybe should that be? I should read the documentation before writing code. I'm not sure what the lambda function is supposed to do, but we will see if return 1 makes it work. Yeah, but now it terminated instantly. That is not good. So wait, return ISL. Okay, technically they say this should work as well, and let's just try it without the lambda. So apparently you can specify an additional condition if you would have a more complex scenario. Yeah, now it works as it should. But in our use case, we don't need to do that. Okay, so let's comment this method out and go for the Windows method. Zack. And as we already saw with threads, the Windows native method is again a bit more writing. Handle event. We can write it being 0 at the beginning. We will later initialize it. So now here we need to initialize it. Create event. Zack. Null. Manual reset true. Yeah. Initial state false, so not signaled, and name no name. And once we are done with it, at some point we'll need to close handle on that. Yep. Okay. And here we start our thread. Where was it? It was already started. Okay, that is not good. We need to okay, let's split those things a bit, because we need to have the element created before we start the thread, otherwise yeah, but then our waiting is in the wrong place. Okay, wurscht. Let's just move it where it needs to be. Someone had a comment?
So I kind of missed why we need a lock for the wait condition.
So I hear you very badly. Can you repeat that again?
Okay. I missed why we need this lock, this mutex for the wait condition.
That's how this documentation specifies it, and this, like, they're using the mutex internally instead of using the event that would only be available on Windows. So mutexes like this, or mutexes in general, you can have on any operating system like Linux, and they all behave more or less the same, while events, actually don't know if we have events of this sort at Linux at all. Normally it's a rather Windows specific sort of things, and what they pretty much just do is they will try to obtain a lock on the mutex and then allow you to release the mutex internally when you make this notify.
Okay.
We can try to step through one of the functions later on to see if the implementation is reasonably human readable or already too complicated. But first we will just use the Windows way of using an event. So I said we had to create it before we start the thread, otherwise the thread would crash. and here we will just want to wait for it. So again, we just use wait for single object. Single object, zack, event, comma, infinite, so we want to wait for infinite, so we want to wait forever, and then in our function we need to give it a body. And here, what was it? I think it was called signal event, or was it set event? It probably was set event. Yep, set event, and then we can just provide the event handle. And the nice thing about Windows events is that they are somewhat more flexible than your typical platform independent wait condition implementation. So here you have these two parameters. Maybe we should quickly say what they do. So the second, well, actually it's the second argument, but the first interesting one here, initial state, that tells us whether the event should be created already in a signal state. So if we would yeah, here sorry, other way around, it's the second one. So the third argument here, the initial state, it tells us, so if this would be true, then we would not need to call set on it, but everything that just waits on it would already be allowed to run once until the event gets reset. So so in principle you could of course just use false, and in the next line use set event to set it to the signal state. That's one thing. And the other argument here, this manual reset, this specifies, actually we probably should set it to false. This specifies how the event will behave once something waited on it. So if we would have manual reset true, then once you have wait for single object, and then you would have a second wait for single object, and a third, and a fourth, and so on. Then once the one thread set makes a set event, then all of the waits for single object would automatically be triggered. While if the reset manual reset is false, then the first wait for single object that succeeds would automatically reset the event to a non-signal state. So if you have manual reset, then you would need to use reset event to return it to a non-signal state. So if this is true, reset event. So you see also in this case you don't have like wake one or wake all. You would need to decide which behavior you want when you are creating your event, because the set event, and usually what you would then do is you would make the set event, and then in the next line you would make a reset event, because everything that is waiting right now when set event happens will then be signaled, and you can reset it directly afterwards. And if you would only, as said, want to wake one, as we did in the other examples, you would just use a auto reset, so that the operating system will just, if you have more than one thing that waits for event, they will just pick one and then wake only this one event up. And usually with Windows it is such that you have a certain guarantee that if you have multiple objects waiting, then they will be woken up in the same order they started waiting for the event, or at least in a defined order. So if you have a multiprocessor system, you could have like two threads on two processes at the same time, asking the operating system to wait on something, and then the operating system would decide which one of those two comes first, but then the order is fixed, so you have the guarantee that everyone will be served. If you are using some simpler methods or something self-made like a simple spin lock, then you don't have this guarantee, and some of the threads spinning and trying to wait for an opportunity might never be resumed, as long as other threads want this resource. So it's generally good to use existing classes or operating system facilities for this, but that should be it. So let's Let's run it and see if it works. I mean, it must work, obviously. Okay, so waiting, 1 second, success. Et voila. Okay, so now we can comment this out, and we wanted to see how, for example, Qt implements their mechanism, their waiting mechanism. That's missing here. So we can put a breakpoint here and a breakpoint there. Okay, so we can get in, stepping through Qt code limits. I have no idea what that's defined, but we don't care for limits. We can just step out of that because that is just part of STL and we know what it does. Okay. Wait condition, wait. It returns -1. Okay, we just went into that. We maybe should not step through things that are not interesting. So now we are in the actual wait implementation within the wait condition. So first it checks whether the mutex is valid. So someone might have just pasted null, in which case it would not work. Now we just get an internal object from the thing. So here, in order to optimize the operation, it seems that they will be using a static object somewhere, which might have a whole queue of elements. Okay, we don't need to step into this. So we have our queue of already working thingies. Then apparently they also check the thread priority. That is something we can talk about later. Then they check that it's not yet woken up. So this is the current entry. Should step out of this. Okay, and while we were doing that, the other thread already went far away as to be able to do this. So now, well, now we are just stepping into another thing, and at some point we'll be able to see how the other execution continues. Maybe we should actually only set one breakpoint and just step through one of the functions, because otherwise it will get confusing. So the debugger actually tracks your step in, step out, and etc. operations for every breakpoint invocation. So that really can get confusing quickly. So here, I think this we can step out. Now we are here, yes. Step in, step out, step in, step, step, step. So we were here. That might have been interesting. But anyhow, so it creates this or rather gets this internal object, and then it locks the mutex. So the mutex is locked. We don't want to step into this, and then on this object, on the internal data object, it will pass the time to wait and the wait condition event, which it created or retrieved from a queue of already existing events, depending on whether we use this for the first time or not. And then we can here see the internal implementation of this thing. So you see it internally uses just like a normal Windows method, the wait for single object, and the event from our object here will be just a handle. So if we try to go back to this, we see that the Windows implementation has just a handle called event, and then a few additional data fields, and it uses a normal event as we used before, which it creates if necessary. So here, basically that's already the whole interesting thing, because now if we try to step further, it was waiting here, and then during it waited here, the other thread made the set event, and then the function returned to us a result. So if we wait forever, then we know, of course, that will never return, but we might have here a wait time for how long we want to wait. So in this case, we want to check the return value of our wait for single object to ensure that we actually waited successfully and not run into a timeout. Yeah, so if it was successful, then we set return to true, and then we can return this. Well, then we unlock our mutex, and then we can finally depost return value. Here, I guess they will be cleaning up unnecessary thingies. So we have an internal mutex. They clear the queue, reset the event, and delete everything that they created. So obviously it's a bit more operations than what we would have with a handmade solution, and finally we return the return value. And now if we stop here and then see a look into the other function here, there, then we'll see how the other end, in the end it will just internally here retrieve the relevant object. So okay, here first it logs the internal data structure. I should not look into this. Then it makes a for loop for every waiting element that there is. So we might have, of course, multiple threads having waiting on this condition to happen. So it will, for each of them, make a individual set event. So this is in a way, of course, it feels kind of inefficient since they're using multiple events. And if we would run this, well, if we would try to use this somewhere where we very, very often use it, we will see that the performance is not very good. But normally, this sort of wait conditions you only use in situations where you don't expect there to be like called hundreds of thousands times per second. It's just a couple times per second to synchronize some access. So this normally is fine. So I said it checks whether this one was already woken up, which it might or might not be. Then if it's not, then it sets the event, and it notifies that this particular element was already notified, and then it breaks because it was wake 1. If you would have wake all, it's the exact same, well, more or less the same loop, just that it doesn't need to check whether it was woken up, and it doesn't break after the execution. And we could try to take a look how the STL implementation looks internally, but my experience with STL implementations usually is that it is very convoluted. So we can try, maybe let's try with the on this side first, since this part of the implementation is usually less complicated. I start the thread. I did not start the thread. I started the wrong thread. Okay, so now it should work. Waiting and suck. So let's step in. That is a good point. I'm not sure if so. Qt we installed with sources. I'm not sure if Visual Studio provides the sources for their STL implementation. But since it didn't find it by default, I would assume they don't. Let's Google that quickly. Visual Studio STL source. Well, at least it's available on GitHub. Did that not search? Or did that fail? Let's cancel this. Do we have Git? We don't have Git. Then we don't do it. The sources are available on GitHub. I will post the link into the chat. By the way, can you now copy out from the chat, or is it still not working? Yeah.
Clicking on the link
Works. Okay. Yeah. So if you browse the, basically you would just check out the source code, and then once it asks you for the path, when you step through it, if you're interested how it works, then you can provide one of the files, and usually then it will recognize the other file, so it will not ask for every single file again and again and again. But I guess for here it's not really interesting to step through the STL implementation in detail. So that much to these wait conditions. And what we should forget to this. And as said, normally what you would usually do is you would have multiple threads waiting for this. So let's maybe add here some additional threads that would do the waiting. So the first one I would say we'll just ignore, since this one is not very efficient anyways. We'll just let's call it my waiter. And here we just can copy the code that we need at Qt. And then we'll start just a couple of each type, and each of them needs to print something. Each of them should say waiting and success. Okay, so I could be lazy about that. Yeah, let's be lazy about it. That's convenient. So we just make a loop. Here we just make new. So if we make a new STD thread without saving the reference, we will not be able to wait on it. But this is fine, I would say. Okay, so this is one, and then we can do the same thing for all of them. For STL and for Windows, and then here we will also put the wake up thingy into a loop. Well, I'll make it even simpler, like this. Okay, we can do the same thing for our STL thread. Then we need a STL waiter. STL. Let's quickly comment this out for now, the Windows version. Zack. Okay, we can now quickly run this. So it will not yet do the Windows part. It will only run the normal. It should now say something's. Did it work? Should be started and it should be doing things. Why isn't it? Did we forget something? I don't think so. Also says only waiting once something's broken. E is lost. Okay, we forgot to print things here. Ah, shit. No, that's fine. Waiter. Ah, damn it. That was, here we need the waiter. Too much copying and pasting is very error prone. Okay, almost. Yeah, we need to give them different names, obviously. 1, 2, 3. Waiting, and every second 2 of them say success, so this works fine. And now let's look how to do that on Windows. So as I said, with Windows you have the thing that this set event will signal everything that's waiting at the same time. So there the behavior will be different. It's like always a wake all. You cannot really make a wake one with this Windows facility. What you could do, of course, is you could add a mutex. So we could do that quickly. Where we could theoretically use. Well, could we? If we use a mutex, the downside will. It's actually not elegantly to be done. If we want the ability to have to wake only one of the waiting threads, then we really would need to create one new event for each waiter, like it's done in the Qt implementation. So I guess this part we just leave for STL and Qt. Okay, maybe here let's then, yeah, that's fine. Yeah, I think this is everything that one can demonstrate about those mechanisms for now. One thing what you can do in Windows which you cannot do in Qt is you can wait for multiple events, and the semantics of this is that you are waiting for like you provide a list of events you want to wait for, and if one of them is true, then the thing resumes. So actually we could demonstrate this. That would be nice, especially since this is something that, as said, you cannot do, as far as I know, with all these standard synchronization primitives that are provided, or rather waiting primitives which are provided by the typical libraries. So we will again create, we'll need to create a couple objects. Let's maybe create a new project for this, or we will do it, yeah, let's do a new project also. Let's do it like this. We will just put this into a if 0 hash and if or else. Then we just make another main. So I don't want to just create a new project for this demonstration, so I will just have everything duplicated within here, since those things yeah, if are the same. So we will need a couple events, so we need an array of events. Let's say yeah, 10 events. Then we will want to have a how do we do that? Yeah, we will do it in the main function first. So first of all, we need to initialize them. So for oops, typo. So okay, so here g events from I is equals create event null false null. Yeah. Okay, so here we have our events. At some point we will want to close the handle on all of them, and in the meantime we will want a loop for wait for multiple objects, count 10, comma, that will be the array of the handles. And now we can select whether we want to wait for all of them or just for any of them. So let's say wait all is false. Let's quickly check. Let me check the documentation if this is really the way this is supposed to be used. Not that I see something wrong. So wait all. Yeah, it is as I said. So we say false because we want to return as soon as any of the events is signaled. Milliseconds infinite, and it will return. We will have to look on the return value. So what does this return? Double word equals sorry, we don't need a code block. We assume this will always be correct, so just check if return block is larger wait object 0, which is defined as wait status plus 0, which is 0. Okay, so just greater 0. Usually below 0 indicates an error. You can check, for example, other optional return parameters like wait and failed. They probably will be negative, or okay, or they are very high, so we cannot wait for arbitrary many elements. That can also be. This one is just -1, but this means that there will be a max value however many elements you can wait for, because otherwise the system will not be able to notify this correctly. So let's see. So if that is ungleich timeout, or rather if timeout then continue, if failed then break, and otherwise we will be able to get the index of the event. So index is index equals object what was it, return minus object 0. Let's add here somehow a breakpoint, or let's print something out. Q event signaled. Okay, Streitpunkt. So this is this is that, and now we will also need some threads which will synchronize signal the events, which we can also create here. Right. We'll just start 10 threads randomly, and they will all each of them will after a random wait period signal one of the events, but therefore we need an argument. So let's say I int I srand I, it's not a great seed, but why not, srand I, and while rand modulo 100 is not null, sleep for 1 second, and if then we want set event g events from I. So it will wait for a random time. Okay, that's probably too much. Let's go with this. And then it will signal the event it's supposed to signal, and that thread will then terminate. And each time one of the threads signals something, you should execute this loop. Actually, we should count down how many executions have been made. That we can terminate after the last one. I++. Assuming all of them will be signaled at some point. Of course, here we have a resource leak since we are not clearing this elements from memory. We should normally initialize here an array where we put them all in. Or we could use a Windows style thread. Maybe let's do that. So null, comma 0 to default. Start address will be my thread, but I will need to change the function signature, comma lp void I, comma null, comma null. Okay. Handle is equal to this, and we can close the handle outright. The thread will remain running until it terminates. Okay, and then we need to be this dual twinapi lp void param, and int e is equals int param. Okay, this is a correct code without any bugs, I hope. Let's see if it compiles and runs and does what we want. Okay, something's wrong. There is at least... Okay, we must return a value. As you see, now randomly different events are signaled. Apparently my randomness is too random, it takes too long. But at some point they should have finished signaling all of them. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, one more to go. And the program will not terminate because it will be stuck in this line, but we can still wait. And now it signaled the last one and we entered this line. And what we also could do here is we could start another thread which will wait for all of them at once. So my waiter does not need any arguments, it can just be null. So we copy this, my waiter, and here we just copy this line. Well, we copy this block for now, maybe. So this we change to true, meaning that we wait really for all of them to work. And if it's not timeout, we ignore the... Okay, we should not. So if it's failed, then just return -1, some error code. If it's not timeout, or maybe actually we could do it like this. If it's timeout, then return -2, another error code. And else return 0, and here right will print a line. Let's copy this thing. All events signaled. So yeah, suck. So okay, maybe one more change. I will make the random condition faster. Let's go, or the sleep slower. Well, it's the same thing. That failed. Why did that fail? Or did that thread not have time to execute? Okay, that should have worked. It should have signaled. Waited for all of them to be signaled. Let's see why. It's always good to check the documentation, but it says set at signal. It doesn't really say that they need to stay in the signal state. Let's try this. It might be that since this one is resetting them, that the wait for multiple object does not want to work with that. So let's quickly see if this is the case. Yeah, and now that was an error, was it? It returned one of the errors. Failed. Why wouldn't that work as this documentation says? Okay, we can try to set here manual reset to false, so that it needs to be actually reset, and see if this helps. Sorry, to true. We should want this needs to be true. It was false already. So now each time something gets signaled, the event will stay in the state, I think. Now we should have set the breakpoint probably. It still fails. Okay, I'm not sure why this does not work. I would have assumed that works with any event type. They should all be signaled at some point. You can try get last error. Get last error. Let's let it run and see why it doesn't want to work the way we want it to. Error 6. Get last error codes. Error 6 means invalid handle. Wait, did we? But we created all the events and then we started the wait. So that should be fine. They should not be invalid. And all of them are valid. I will check why this doesn't want to work as described. So the wait for multiple objects you can use with different types of handles. Perhaps there is some footprint somewhere that it doesn't like the normal event. So for example, you could use this to wait for multiple processor or multiple threads to finish as well. So this wait for multiple objects is simply a very generic function. But I would have assumed that it should work just fine with the single oh, I know why. Sorry, that's a stupid mistake. Of course they are invalid because if we comment out this part of code, then this will close our handles instantly. So let's keep this code, but keep this set to true. Then it should work with this event type. It says event 1 was signaled, but this thing here, now it didn't trigger at all. Interesting. Okay. Okay, but this also waits for all of them signaled and then closes them. I guess we should ensure that we will not terminate before this thread is finished. So let's make here wait for single object H. So now, oops. So now we are definitely sure that we will not invalidate the handles before all of them have been signaled. Yeah, that's what will be happening here, I guess. But then we can comment this code out, since now we have our waiting condition for the thread. And it's waiting. And all of them end 0. 0 means success. Nice. All events signaled. So this worked worked out just fine. Now with this code it will also work. But before we enable this code, I would want to check if this would in principle work here. Oh, actually probably it would work in any case, but we just closed the handles too early. That was why it didn't do what we wanted it to do during the very first test of the code, all events signaled. Yeah. Because here now they will be reset because they have woken up something, but I would guess that this still should successfully signalize the multi-object thingy. But I might be wrong. Let's see. While it's still waiting, was it 10? 1, 2, 5, 6, 7, 8, 9, 10. Okay, so indeed it requires, which is not said in the documentation, that all of the events must not just be signaled, but also stay in the signal state for this to unlock. So if we have here a false, or we are already doing something that would reset them, then this doesn't work. So let's go here for true. And then it will work as expected, except of course that this... No, wait, this is not good, because then all of them will say the same thing. You would somehow need for this loop to really behave nicely, have a basically remember which events were triggered and not query and exclude them from the array. This is unnecessarily complicated. Because each time we enter here, if it is already signaled and it wasn't reset, it will then just say that it was the first element which it found. The problem is that we really would need to have a nice array and remove elements, because we cannot just replace individual entries with zeros. Okay, so let's do it like this. Since we want to have a nice example, so make and if wait all, then we'll have one example, and if not wait all, then we will use the other example. Yeah, so this at least leaves us with a consistent sample. So if it's false, then it will just go to the lower route, where it will print for every of them a line and finish once it's done. And if it is set to true, okay, this was everything. And if it's set to true, then it will go the route mentioned before and wait here until it finishes, until all of them finish. So now at this point, this behaving this way, we would not need to have a separate waiting thread used, since we cannot do anything here anyways. But I will leave this as an example how to wait for a thread to finish. Anyways, so any questions? No questions? Okay. So since we did not have any break and there was normally supposed to be one, 15 minutes long, we can finish today a bit early. If you have any questions, then ask them now. You can also ask them later by email. I will upload both projects, the test multithreading and the test wait, to Moodle. Here I will enable the uppercase to be the one used by default, since this is the one that demonstrates the different methods that you can use across different platforms. And the lower part here will be disabled, since it's a more Windows specific sort of thing. So if there are no more questions, then we can stop at this point. Okay, then everything is clear. Let me ask a question.
Well, until now, but I think I have to take another look at the code. If you could upload it, maybe then I will have some questions for the next.
Okay. There was one more thing I could show you, namely using this named, but this is boring. You just can, so instead of making a create event, you can use open event and then you just specify the name. So I don't think this is something that at this point we need to look into. Yeah, I will upload the things. So 2 projects. I create a task for the homework where I will again write down exactly what the homework is, which mostly will be just a copy of the to-do that I wrote in here. And I will upload the recording to YouTube and put a link on Moodle. So see you next week. Bye bye.
Thank you. Bye.
Thanks. Bye. Bye bye.